Ladies and gentlemen, it's my great pleasure to present some of my results here. And the electrochemical conversion of side streams coming or originating from pulping factories is something which occupied or fascinated my group since 10 years. It was a smaller fraction of my group, but it was steadily evolving, and you will see that today. Why we should focus on electrosynthesis in general. As you know, our company decided not to have nuclear power plants anymore. In next year, we will shut off the last one. And also, we try to avoid CO2 emissions. That means coal and gas firing will be switched off as well in the near future. That means we have more and more regenerative electricity sources, wind power, photovoltaics, solar thermal stuff. Hydropower is really small, and even biomass is small. Therefore, you can feed into the electric grid, and unfortunately, the supply doesn't fit to the demand. And the question is, what can we do with that? One possibility is that you have a big battery. But if you think about the electricity we need at the moment, and this is growing because more and more processes will be electrified. At the moment, you have 2 terawatt hours daily. If you know that, then you need one of the biggest lakes in Germany, and you lift it up 400 meters. This is virtually not possible. That means the other way is that you have more electricity, and the surplus of electricity is used to make valuable chemistry out of it. It can be hydrogen, it can be fuels, but also more valuable chemicals. Because everybody at the moment thinks about value-added products, and one thing is synthetic fuels. The problem is here you need a lot of electricity, for example, to convert CO2 to alcohols or alkanes. And the problem is that the bargain will be pretty small what you make out of it. It's much bigger for commodities, and it will be definitely of interest for fine chemicals. There are 2 things which are usually ignored by many chemists in this area, and one of them is the selectivity. The selectivity is often not so big problem for synthetic fuels, because here you can live with some isomers and even some mixtures. For commodities, precursors for polymers, here you need a certain selectivity, and of course for fine chemicals like APIs, you need a really high selectivity. And the second argument, which is often forgotten, is the downstream processing. This is virtually the killer of many processes. That means if the downstream processing is too expensive here, you cannot afford very much. But if you go to fine chemicals like APIs, there you can even afford maybe a chromatography. Therefore, you have to find an easy way to handle the electrolyte system. And this is usually our focus at the very beginning already, that we find a suitable downstream processing when we have a electrochemical operational window established. The compounds which are in there, and usually some synthetic fuels, everybody's talking about that, higher alcohols, but at the moment, cost efficient might be this area and this one here. We summarize that at what point electrosynthesis pays off, and then you will be maybe not so enthusiastic anymore about methanization. Therefore, there you need the electricity more or less for free. Why should we focus on electrosynthesis? And this is these are the buzzwords which came out of the chemical engineering news. It's inherently safe because you bring in the electrons and take them out with the other electrode, and that means more or less as soon you switch off the electricity, the reaction ceases immediately. That means there's no thermal runaway reaction. You can avoid some metals or critical resources. Since you only take electrons for activation, the substrate, you do not have reagent waste. And of course, you need some solvent if you're unlucky, some supporting electrolyte or mediators. But in most cases, you can avoid some waste. And this is very appealing to industry at the moment. Of course, you can adjust the reactive power. In most cases, you don't need that, because the most reactive will react first, and therefore it's not so difficult for that. It brings up new synthetic approaches, shortcut of many steps, and it also creates new IP space. This makes it different to other conventional techniques, and of course this is the reason why many companies at the moment jump on this field. These are more the typical buzzwords we have: power to chemicals or green aspects. The American call this disruptive technology or game changer. I'm very convinced that this is the case. Usually as organic chemist, you have this kind of container, the round bottom flask. You put in your oxidizer or reducing agent. Here we just have the 2 electrode arrangement. And if you do so, then you see in euros, you need here per molar conversion. That means 2F. That's a reasonable assumption that you make a bond. You need 2 electron equivalents, and relatively conductive system. That means the applied voltage is 3 volts, and this corresponds to the molar amount. And most reagents are much more expensive. This corresponds as well, if you think about kilogram product, to 0.5 to 6 kilowatt hours. This is if you do methanization. This is if you have a polymer system. What can you do with electrosynthesis? Oxidation and reduction is more or less trivial, but you can start radical reactions or sequences, or generate bases, because you make a radical anion, and this could be have a basicity like butyllithium. And but the problem for electrosynthesis is often you have to accumulate your final product. That means here you reduce, here you oxidize. In the worst case, you shuttle here, and then you have a full reversibility. Then you have to separate this kind of compartments. And one way is to design the following up reactions in a way that you do not have reversibility. That means control of the following up reactions is very important. It could be that the product is eaten up by the counter electrode, but also at the same electrode on a longer time scale. And this is not reflected by CV studies. Therefore, you have to test this. You have to do electrosynthetic testing. And what is the important thing about that? Well, usually in the textbooks, electrochemistry is taught by a physical chemist, and everything happens on the electrode. In organic chemistry, electrosynthesis is a little bit different, because the radicals are quite stable. Then you have intermediates, and the intermediates have an afterlife, which is more not on the electrode, but close to the electrode or in bulk. And then you have some arguments or parameters which are very important, that you have an inert electrode or electrocatalysis involved. Of course, the potential plays a role, but also the overpotential. Overpotential means there's some arguments why some molecules cannot go there or hindered to be converted. In this area here, which goes into bulk, the supporting electrolyte is very important, but also ionic strength, solvation, temperature, flow, and so on. But there's one number which combines both of them. This is the current density. The current density tells you how much radicals are formed close to the electrode, and the concentration of radicals determines which pathway is populated. And if you know this, then this number combines both sceneries, and you can easily work with that, because this is also indirectly controls the potential. And then the setup becomes much easier and is scalable if you can work with this number here. Therefore, we early started to do a screening with product-driven criteria. And this is a compromise to make enough electrolyses on one magnetic stirrer, but in a good, accurate way, because here the dimensions are very clear. You can even use that later on for optimization, because in a more advanced screening technology, you don't need only yes or no, you need precise data. And therefore, we start here. We have 10 different electrodes. We usually start. We have more than 50 now in stock. With electrolyte, you can choose everything which is conductive. But the problem is we have earlier at that point already to look. First of all, it should enable the conversion, but it should have no environmental constraints and no safety issues. And of course, the costs are also an argument. Therefore, we have usually 5 to 8 which do the job, but around 200 which are usually feasible. We directly look into the system if the product is accumulated or not by GC or by LC, and couple this with mass spectrometry. This is divided cell, but also the undivided cell. Then you can place a little bit more of these electrolytic cells. And since the data are quite accurate, which will come out that, you can use that directly for design of experiment. You will see this later, and also machine learning. I would not call it artificial and KI. This is not true. It's machine learning. And optimization is done if you have the different things here as well. You can make it your own, or if you have not a machine shop with that, it's also easy to buy at the moment at ICA. This is these are the undivided cells. We have 8 of them on one magnetic stirrer. And then you can screen here. And after that, you know, a small scale directly which kind of larger cell you can use. Typical batch type cell on divided cell, also called half cell, or you screen directly in a way that you jump here from this here to this one here, and then you have 200 grams directly of the final product. This is a factor 300 from screening directly. If you go to larger scale, there's no way out that you use a flow cell. This is the smallest part of the laboratory. Then you pump overnight through the flow cell in a container where you do later on the workup. But then you need, of course, a little bit more powerful periphery. But more or less, this is more or less like a kilo lab in industry. And the electrolytic cell here is just an add-on. Therefore, the backbone of our electrochemical development is the screening all the time here in batch. And at that point, we have to decide if you go to the flow cell, larger flow cells. This one has a power consumption up to 5 kilowatt, and which is in our laboratory the end. Or you go into the kind of stack cell. In batch type, and then you can go at least to a kilogram size. But this is usually the very end. In most cases, this is enough. Let's come to the pulping process and what are the science streams. Especially the Kraft process is the biggest at the moment, which is used worldwide. And I think it's not necessary to mention it to you because you're the experts in that. It's usually done because of the cellulose. It provides the best cellulose fibers usually, and therefore it's done on a large way. There's some black liquor in the workup stream. You have a side stream which contains lignin, hemicellulose, and the turpentine fraction, and so-called crude tall oil. And these side streams are in most cases just incinerated to get back the inorganic process chemicals. What we have a look now is on this part here, sorry, on the crude tall oil. And we do a Kolbe electrolysis on that, and we take it, have a look at that. What is Kolbe once more? Kolbe is one of the oldest electroorganic syntheses. It's usually done on a platinum anode and low pH, high current densities, and was already found by Hermann Kolbe 170 years ago. Often this is associated with Michael Faraday, but Michael Faraday did not know what he was doing at that time, 20 years before. But Hermann Kolbe was the first who identified what's going on. Hofer and Möst used different electrodes and switched to a high pH. That means a salty system. And under these conditions, you go to the cationic species, which is trapped by a hydroxide or by the carboxylate, and then you get either the alcohols or olefins or the esters out of it. What we did here was that we used the tall oil fatty acids, and we did decarboxylation, and we did it in a way that you get additional double bond. What is the reason for that? Usually there are multiple unsaturated, and this gives us the possibility to make epoxy units out of it, and it just adds an additional epoxy unit and makes it as an interesting building block for thermosets later on. How does it work? We could work here on graphite systems with a relatively moderate current density in an undivided cell, and then you have to anticipate this kind of intermediate, and it usually makes very quickly the elimination. A little bit of stuff is trapped by methanol. This is usually controlled by the so-called iodine number. The higher the iodine number, the more double bonds you have in there. Unfortunately, this is German, but I guess you can read it even. And you see the orange stuff means after electrolysis, you enhance the double bonds, and this is the stuff which is expected. And then we went directly from a small scale to a larger scale. And you see that here, this is the way how you do this. It's a kind of a stacked electrolyzer system. We did not use the bipolar version. This gives us a lot of gaps in between. And therefore, we had a anodic surface here of 370 square centimeters. It's typical isostatic graphite. And you operate that. Therefore, you need a little bit larger power lines. It's only 5 volts, but 7.5 amps. And it directly converts 200 grams of TOFA. The nice stuff with that is we have a very simple downstream processing, because the stuff which comes out is very apolar, and therefore you can easily extract it. There's no chromatography, even though distillation is necessary, and the solvents which come from the rotivap could be directly recycled and used. We were able, after epoxidation, which what we used here is just use a ketone and oxone to get the epoxy derivatives out of it. And you can make here thermostats out of it, and you will see, as expected, especially this system and this system gave a more stable thermal system, and you can use that compared to other systems which are out there. This maybe needs a little bit more to get to higher temperatures, but you see a clear trend, and it's a clear behavior. That means if you have something to fix, this would be a perfect material for that. Well, let's have another look on the what's in there. That's the lignin, and Kraft lignin is something which is abundant there, and sometimes it's isolated and then pressed in pellets to use it for heating. But in most cases, it's just concentrated as black liquor and goes directly to the incinerator to make either electricity, which is in Germany still highly subsidized, or on the other side to make steam, to make heat out of it. Well, it's major part of plant biomass. It's, besides cellulose, the second most abundant biopolymer, and it comes from units which are so-called S units from Syringol, which is in there, guaiacol derivatives, or you have at this point here the hydroxy benzene subunit. Nature does most likely a radical cyclization, and you have a high diversity, and a high diversity is the reason for that, because it's a kind of a defense wall against fungi. The high diversity makes even it difficult for fungi to break it up. Well, if you do the pulping, then you see the enormous amount with 130 million tons per year where wood is converted. It's a really large process, and this brings you to a significant amount which has almost petrochemical style. Therefore, you can get the Kraft lignin, but only from a few processes this is isolated. If they use just the CO2 from the flue gas, they purge it in, and then you have a kind of boost process where you can isolate that. Usually it's washed, and afterwards it's just dried up, and the more dry it is, the more expensive it usually comes along. Well, is there something we can do, make chemicals out of lignin? Well, the oldest work is maybe by Freudenberg, more than 100 years ago. And the most reliable way, which was rediscovered many years ago, is that you use nitrobenzene oxidation. This is usually the standard if you have lignin, to know how much vanillin you can get out of it. It's not something you would use for the production of vanillin, definitely not. But it's the most reliable way because the nitrobenzene dissolves the lignin, and under these conditions, 170 degrees, 10 bars, you get usually out of Kraft lignin less than 10% vanillin. Why is it not used? The reason for that is you generate some anilines, azo compounds, azoxy, even nitroso compounds appear in there, and you don't want to have this in something which you put later on into food. Therefore, this is just as a reference reaction. Well, if you look at electrochemical conversion of lignin, then you will see this is something. At the very beginning, we want to do something in the laboratory which does not need very fancy setup. That means typical undivided glass cell, and you are looking for that, and no cancerogenic chemicals, and at least nothing we add to it, because only a part will be converted, and we don't want to have material which ends up in the remaining lignin. And use electricity as sustainable oxidizer. And therefore, the question is, how does it work? It turned out the best way to do this is that you have an active electrode. And the active electrode is that you have, for example, nickel or the other metals. On the surface, under alkaline conditions, you have a nickel oxide hydroxide, and this is a strong oxidizer. And this lignin is then converted, make a lignin plus, something like this, and this disintegrates and forms vanillin. And you see, this was found some years ago, and here you see this is already in a way that we can say, okay, this is easy to handle. When we were playing around, and then we saw it's possible that you use other things like nickel as a base alloy, which allows to make the nickel oxide hydroxide. Basically, this could also work with iron, but iron is very prone to corrosion. Cobalt is the best version you can have. But there are two things which are difficult with cobalt. One of them is the cost, then you have corrosion, and the other thing is cobalt alloys. Here, if you use them like steelite, they're one of the hardest alloys you can get, and it's even very, very difficult in the machine shop to get it cut in the right direction. Therefore, we were standing with nickel, and it turned out that nickel anodes are corrosion stable. The vanillin yield was not very high. We used planar at that point, and the current densities were not too high. Therefore, we are afraid that the space-time yield would be too low. And therefore, we went to the nickel foam. The good stuff for nickel is because in many battery aspects on plating applications, nickel is used. And therefore, you get all different morphologies out of that. And we took the nickel foam anodes and behaved the same. And here you can apply higher geometric current densities. That means from a square centimeter here, we can apply much more than here. We cannot say what the current density in detail is because it will be differ in the depth of the foam. And of course, we do not know exactly the surface at a certain spot. But however, this works really nicely, and you can tremendously enhance the speed of the electrolysis. Then something turned out which was very, very unusual. We started with a new electrode, and it turned out if you have a new electrode, just my computer is at the moment a little bit slow. A new electrode, then you see at the very beginning, you see that the new electrode gives small yield. And if you operate the electrode before in black liquor, which is a horrible mixture of many, many other compounds, the black liquor usually contains things like alkaline materials, some sulfur stuff as well. And it turned out if you operate it in the black liquor, the electrode became better and better. And if you operate 4 times in black liquor, then it turned out that the system works much, much better. And if you work it 9 times in black liquor, then it's almost like a perfect stability of the electrode system. And the question was, why is this the case? Why it becomes better when you work it before in a dirty black liquor mixture? And it turned out we were thinking about maybe you have some lignin fragments on the surface, which maybe help in the conversion. And it turned out you need an analytical system to work on that. Maybe there's some electrode fouling, and the way to do this at the time was FAPA MS. That means flowing atmospheric pressure after flow. This is the one which generates here at that point some oops. Some ions, and these ions operate like an APCI, and you do ionization, and the small molecules will be lifted up. And it turned out there's a molecule in there with a mass of 123. And the other things which you see in the mass spectrometry is usually something which is with some other cations, a combination of a dimeric, trimeric, and other things. And the question was, what kind of molecule is this? And it turned out that this is something which is not we expected. It's not a phenol or conversion of a phenolic system. It's something which we definitely did not expect. It's a diaminotoluene derivative. At that moment, we were shocked. It could be maybe a cross-contamination from other laboratory experiments. But it turns out it only appears if you have the black liquor in an undivided cell. Most likely it comes from a peptidic precursor, and it generates the system. And by mass MS experiment, you could easily show that this definitely forms the system. And if you add this specific compound to the mixture, you have the same effect like the pre-treatment with black liquor. And therefore, you see the what we call activated anode is here below. Then you see the red spots. It's much better, and if therefore it makes sense to add it. At that point, we had 1.7 weight percent vanillin out of the lignin. And the question is, can we go even better? And it turned out, if you go to higher temperature, it increases as well. And therefore, with the knowledge we had before, we went just to higher temperatures now. And this was maybe more or less the key. What is the reason for that? You have usually an oxidation of the lignin, and the particles interlinked, and it's not floppy enough. And if you go to higher temperatures, then it starts to liberate the vanillin. And you don't want to have liberated at the very beginning. You want to do the oxidation and then liberate the molecule, and this allows that you do not over-oxidize the vanillin. And this is one idea what you can do behind that. And here you see we had a look at that and had a look what is the, first of all, what gives the nitrobenzene oxidation here. This is the standard. It means this tells you how much of the vanillin could be obtained out of the system. Then you see the UPM material is not so good like the other ones here from Westrock, but however, this should be the range we can expect. And therefore, for the initial optimization, we used the other one, which was not that good, and to get a very robust process. When we started that and we used that, and then you see these are the nickel foam derivative we used, and you see you could even double the previous experiment. It usually comes along with acetovanillone, and if you compare this to the NBO oxidation, that means the nitrobenzene oxidation, it's 60% relative vanillin yield. Therefore, it's already a very good result. And it turned out we do not need foam anymore, because at 160 degrees, the kinetics are so fast. Therefore, you can even work with planar electrodes, which makes it much easier to get it and to install it. Therefore, it's the same yield. Even if you have a planar system which is laser crafted, it ends up with the same yield. Therefore, it has not much influence anymore. Well, what we went then to different Kraft lignins, and one of the best we could use here was indolane 8T. And here with the nickel sheet electrodes, you see it even went to 4.2 weight percent, and in almost concurrent version, the acetovanillone also started. And you see that the number is very similar. You have almost 60% relative vanillin yield, which the nitrobenzene oxidation provides you. And at that point, we had a look, and here you see that summarized the different things, the yields we had, which was published also last year in ACS Sustainable Chemistry and Engineering. Sometimes it's in electrochemistry a problem that you want to do something, but an intermediate is much easier over-oxidized, and then you cannot make it to the very end. And if this is not compatible, then you have to think a little bit differently. And one way is that you go to the Excel version. That's the in cell here. That means we had everything is working in one part. And the Excel would allow you that you make a reagent, you generate by a flow cell, you separate off the byproduct, and then you add it. This is all the time the way to do if the substrate is not stable towards the electrodes. And here you can work with much higher yield, milder, and liberation. You just separate the electron transfer here from the organic transformation. There's one oxidizer I want to show you. This is peroxide dicarbonate, and this is something you can do. You can have even a reservoir which allows you to have fluctuating electricity consumption, and but still can do the organic conversion in a reliable way. Well, this is a very old chemistry. Once upon a time, it was done many, many years ago. And if you look at that, it's more than 120 years ago when they made it. And what is the reason behind it? What did they do? They use carbonates. And if you have carbonates, you oxidize them on a relatively brutal way, and the oxygen-oxygen contact is formed. This allows you to make this compound. You see, this is very, very specific. You cannot use that for an efficient synthesis. The structure was verified many years ago. And with the use of bond or diamond, you're able to make this kind of compound a little bit easier. Keep in mind, the peroxide dicarbonate is not something where the typical percarbonates. Percarbonates are just complexes with hydrogen peroxide and carbonate. And this real peroxide dicarbonate protein is electrochemically only accessible and has unique reactivities. If you generate that, you have to do this at low temperature, and then you add this to the lignin, do the oxidation, and then you heat up. This is the idea behind that you have also you separate the oxidation from the depolymerization event. The oxidation, you see what you do here. You work in aqueous media, and you have the undivided cell. You have a stainless steel cathode, which serves even as cooling. And by this way, you can make easily this kind of material. Unfortunately, you cannot store it for a long time. You have a concentration which goes far beyond 180 millimolar. But you take more or less CO2 to make an oxidizer, which is really an intriguing part. Then you can use a larger electrolysis flow cell with a bond-up diamond, which is commercially available. And then you can get large quantity out of that you can make the conversion. Here, you can try to get to higher concentration, but if you go to higher concentration, the problem is that the current yield is lower, because you enhance it, but also some decomposition occurs in there, and oxygen evolution is a byproduct. Well, then we use that, and we use it for the lignin depolymerization. We have an oxidation, and the other one is a degradation, thermally induced. That means a two-step sequence. And then you see why this is of interest. It gives you much higher yield. That means that the same system we had before, now we have at 5% and 2.58% of the acetovanillone. And that means it refers to 91% of the vanillin yield by the nitrobenzene oxidation. I think we are already quite close. And maybe the other thing is, which is very important here, you generate as a byproduct sodium carbonate, and sodium carbonate is a makeup chemical for the system if you use the inorganic process chemicals. Therefore, I think it fits directly into the process there. The optimization is very interesting because here we used already the DOE. I'll show it quickly to you, that we had the amount of podic and the time of thermolysis, and the temperature of thermolysis was very important. And we had a look at that, and turned out that here the heating time is important, but the temperature itself is very important. And the amount of podic has virtually almost no influence. And this turned out that you just have to look that you use a minimum out of it, of the podic, and it becomes much more energy efficient. The important thing is here that you see the amount of podic can be reduced here. You're still in the dark green region, and if you use less, you get the same yield. And indeed, it was the case. Even the yield went a little bit up. We went to 5.5% when we went into this area here, and therefore the quality was quite good, and the energy which you here apply is less efficient, less intense, and therefore more efficient. We ended up here even with inulin AT with 6% and 1.8% of acetovanillin, and almost at the range of 90% of the vanillin yield, which is by the NBO version. Therefore, I think this is electrochemistry catches up with the nitrobenzene oxidation, and here you see the relatively yield and the absolute yield in weight percent. Well, just to show you, sorry about that, very quickly how clean this is. This is a GC of the crude material. And then you see the vanillin, the green indicated one, acetovanillin. We have a little bit of vanillic acid, and there is some internal standard, but the selectivity is quite outstanding. And if you use this or wrap this up in a point, then you see you can do it at low temperature. Then you have 1.7%, or go to high temperature, and you increase it almost by factor 2.5, or you go to the so-called two-step version with podic, and then you end up with a much higher yield. Well, I have shown you something which tells you we can make 3 to 6% of interesting molecules out of it. But the problem is we have a lot of large amount of unreacted lignin. And the question is, can we enhance the degradation, or can we recover the interesting products without neutralization of the whole solution? Because the caustic soda you need there eats up 2 to 3% of vanillin by the pure cost. Therefore, you need something which is more smart to isolate this. As I told you, the downstream processing is the killer of many electrochemical processes. Therefore, you have to look at that very, very early. And the idea is that you adsorb it on a system, and then you have the next cycle and can go further. And the idea is very, very simple, that you have a solid phase extraction by an ion exchange resin. Because you deprotonate the vanillin, and they have the vanillate, this goes onto the resin, it sticks there, and even more caustic soda does not rinse it off, and therefore you have to protonate it first, and then you can rinse it off, and you have a concentrate of the vanillate. And this works really in a really nice way, because keep in mind, this is smaller in resin, which is a gel type version, and it just excludes all the bigger system. Only small molecules will be incorporated here. Therefore, why does it work at very high alkalinic concentrations? Well, the reason for that is very simple. You have an organic system. It makes all the different interactions, Coulomb, van der Waals, and pi interaction. And as soon you get more and more ionic, then the Coulomb interaction is less, but then the other ones increase. Therefore, you can only remove that if you protonate it and rinse it off. The simplest resin which is available and which is used in these water filters is possible, and you get 90% of the vanillin out of the system in a very good way, and therefore you need a little bit more bad equivalence, but it works nicely, and it's an efficient way without disturbing the whole process. Even in black liquor, this is possible, and then you don't have only vanillin, you have also also guaiacol and acetovanillin already in there. There's a small amount in black liquor of Kraft process, 3 milligram per milliliter, but if you look at that, it's enough if you can have 1 or 2 plants where you can treat the black liquor, then the world market of these chemicals is more or less flattened. You could show that you have 74% of the aromatic phenols out of this system. And the interesting stuff is if you rinse it off, you find another one, which is not visible so easily. It's a stilbene derivative, which is used for photoresists and many other applications. And you even can oxidize it and get vanillin out of it. But this has a perfect fit on the solid phase system on the ion exchanger. Therefore, the amount you get out of the black liquor is 1.6 milligram, which is per milliliter not so bad. You can even remove the small molecules and then do an electrochemical oxidation, then you get this once more and can get it out of it. That means you have, by pure absorption from the black liquor already, these molecules. By oxidation, you only get mostly vanillin selectively, and then you have this adsorbed. And since all of them have different pKa, you can just have a program how you liberate it, and by this program liberating that, then you separate them also. That means you get them almost clean off the column, and by this way you can go up almost 2 milligrams per milliliter in black liquor. I have told you that the electroconversion at my condition is possible to get the selective degradation of Kraft lignin to these molecules, and especially vanillin is, of course, the most interesting one, but this one is also not that bad. And you can get them also directly from black liquor. The good stuff is that our process does not disturb the waste streams, and even the PODIC one is the good way to have makeup chemicals. And of course, these are novel concepts to use PODIC, this novel oxidizer, and the temperature program that you separate the oxidation from the degradation process is very important. It's the key to get high yields. You can catch the final product by the solid phase extraction, and the important thing is that we all the time we have a look at that if we take out chemicals, we do not disturb the big picture. That means the major chemicals you have in there, it's not big because you only make heat, you only get the inorganic base back. Well, I did only very little of that, and this is my group last year doing skiing, or 2 years ago doing skiing already. And Caroline Regenbrecht started that in my group. Dominik Schmidt brought it further with my Hartmar. Goswin de Cruyff was the person who did the thermostats. And this is the actual team working on lignin and related systems, also lignosulfonates and all the different versions of lignins. Collaboration material science was close by Mainz in Bingen. Then we had a pulping factory was involved. It was funded by the government, and also one person in my group, Goswin, was supported by the material in science Mainz. This was a school of excellence, and I also thankful to my company we founded 2 years ago. I thank you for your kind attention, and if you have questions, please hit me.